If I told you that these huge AI models, the LLMs everyone's talking about, are actually, well, kind of amnesiacs, you might find that hard to believe.
It sounds counterintuitive, doesn't it, given how powerful they seem?
Exactly.
Hey.
But it's a real limitation. They can't truly learn continuously. They're basically stuck forgetting things almost as soon as they encounter them.
Uh-huh.
So today, we're diving into something designed to fix that. It's called nested learning, or NL.
Yep, it's a framework coming out of Google Research.
And the promise is pretty wild, unlocking unbounded levels of in-context learning. Real learning, basically.
Right. So our mission today really is two things. First, we need to unpack the core idea behind NL. And it's a bit mind-bending, actually.
Right.
It suggests that the optimizers, the algorithms we use to train these models, they aren't just tools. They're actually sophisticated, fast memory systems themselves.
Optimizers.
Well,
As
yeah.
memory. Okay, that's interesting.
Yeah. And then once we sort of wrapped our heads around that, we need to connect this technical breakthrough, this idea of self-modifying AI, to the bigger picture.
The real-world impact.
Exactly. The philosophical side, but also the practical side. How does this change what the sources call the economics of scientific inquiry? How we decide what research is even worth doing?
Got it. And we're drawing on some pretty dense stuff here. Google research papers, academic philosophy on science.
It's a mix, yeah. Cutting-edge AI architecture meets some deep thinking about how science actually progresses.
All right, let's dive in. Let's start with the problem itself. Why can't current LLMs learn continuously? What's the technical block?
Well, the papers use a really vivid analogy. They say these models suffer from anterograde amnesia.
Like the medical condition.
Precisely. The inability to form new, lasting memories after, say, an injury, or in this case, after the initial pre-training phase ends.
Okay, so break that down. How does that map onto the AI architecture?
Think of it like this. The knowledge the model gets during pre-training, all that data it ingested that's like its long-term memory, it's baked into the weights, the MLP layers.
Static knowledge. Stuff it learned once.
Exactly, static.
Yeah.
Now, when you give it new information, maybe in a prompt or a conversation, that info only lives in the current context window. That's its short-term memory.
Okay, like working memory.
Right. But here's the critical failure. That new information in the short-term window, it can't effectively consolidate. It can't transfer and integrate into the permanent long-term structure.
So it's just lost once the context window slides.
Pretty much. It's trapped in the immediate moment, unable to make lasting changes to the core model.
Which is totally unlike how our brains work, right?
Yeah.
We learn something new, and it starts sticking.
Exactly. Biologically, we use what's called online consolidation or synaptic consolidation. When you encounter something new, that memory trace, even though it's fragile at first, starts stabilizing almost immediately.
While we're still awake doing other things.
Yep. It's happening right away, allowing that transfer from short-term to long-term storage dynamically. Current LLMs, once they're trained and deployed, they just lack that dynamic, ongoing consolidation mechanism.
Okay, so that's the problem. Amnesia. And nested learning, NLL, is the proposed cure. How does it work? You said it reframes the model.
Yeah. Instead of seeing the model as just one big stack of layers, NL views it as a set of nested optimization problems. Think of loops within loops running at different speeds.
Multi-level optimization.
Right. And to really get it, we need to refine how we think about memory and learning, borrowing from neuropsychology.
Okay.
So memory, in this NL view, is defined very simply. It's just a neural update caused by some input, a change in connection strength. That's it.
Just a change. Doesn't have to be useful yet.
Not necessarily, but learning. Learning is the process of acquiring effective and useful memory. It's change that actually helps the system achieve its goal, whatever that might be. Purposeful change.
Gotcha. Memory is change. Learning is useful change. And you mentioned levels, different speeds.
Yes, this is really the core idea, the levels. Components within the system are ordered by their update frequency, how often they get updated.
So faster parts and slower parts.
Exactly. You have high-frequency components, these fast inner loops, operating inside low-frequency components, the slower outer loops. It's a hierarchy based purely on speed.
Okay. A hierarchy of update speeds. How does that lead to the optimizer being memory? That still feels like a leap.
Well, this hierarchy perspective leads directly to that key technical insight. Optimizers are associative memory. We usually think of something like, say, gradient descent with momentum.
Yeah, SGD with momentum. Standard stuff. Help speed up training, avoid getting stuck.
Right. We see momentum as just like a simple calculation to smooth the path downhill. But NL reframes it. It says SGD with momentum is actually already a two-level optimization process.
2 levels.
The main weight updates are the slow outer loop. But the momentum term itself, the part that keeps track of past gradient directions that's operating as a high-frequency, fast inner loop, it's its own little optimization process.
And what's its goal? What's the momentum learning?
Its implicit objective, its goal, is essentially to compress the history of past gradients efficiently. It's trying to learn a useful summary of recent updates to inform the next step.
Ah, okay. So by compressing that history in a useful way, that is a form of memory. It's storing past experience to guide future action.
Exactly. It's functional, goal-oriented memory. It's stabilizing information about past activity to help the overall learning process. It's an associative memory because it links past gradients to the current situation.
Wow. Okay. So the optimizer isn't just a tool. It's a learning component itself, a fast memory.
Precisely. And the whole system, all these nested loops from fastest memory to slowest weights, is driven by a signal they call the local surprise signal, or LSS.
Local surprise. What does that mean?
It's basically a measure of mismatch or error, but calculated locally within the network. It quantifies how surprising the model's output is compared to the target right at a specific point.
So it's not just one big error signal for the whole model.
No, it's much more targeted. If a particular part of the network makes a mistake, that numerical surprise feeds back specifically to the relevant memory loops, especially the fast inner ones.
Telling the memory, hey, what just happened here was unexpected. Update yourself.
Pretty much. It triggers consolidation or change only where it's needed, based on that local surprise. It allows for much more fine-grained, continuous self-correction.
That sounds way more dynamic.
Mm.
So how did the researchers actually build something using these NL principles, move from theory to a working architecture?
Right, so they started creating what they called deep optimizers. They figured if momentum is already acting like a simple memory, why not make that memory system more powerful, more deep?
Deeper how?
Well, instead of just using simple linear math, like dot products, to manage the momentum or the gradient history, they started using richer internal objectives within the optimizer itself, things like L2 regression loss.
So giving the optimizer a more complex goal than just smooth the path, like asking it to predict the next gradient or something.
Sort of, yeah. Making its internal task more sophisticated so it can learn more complex patterns in the gradient history. And crucially, they added depth by putting actual MLP modules, small neural networks, inside the optimizer.
A neural net within the optimizer.
Exactly. They call it Deep Momentum Gradient Descent, or DMGD. The optimizer now has its own nonlinear processing power dedicated purely to managing its memory of past updates. It's learning how to learn gradients better.
That's the meta. Okay. And what about the different timescales? You mentioned humans don't just have short and long-term memory.
Right, we have this whole spectrum. Memories seem to stabilize over various timescales, so they built the Continuum Memory System, or CMS, to mimic that.
Their continuum?
Yeah, instead of just two memory stores, CMS is basically a chain of these MLP blocks, like little memory modules, but each block in the chain is updated at a different frequency, a different timescale.
So you have a very fast memory, slightly slower, medium, slow, very slow, all operating together.
Precisely. It creates this spectrum of stability. New information can come into the fast blocks and then gradually, continuously percolate down and consolidate into the slower, more permanent blocks without ever hitting a hard boundary. It allows for perpetual transfer.
That sounds like it could actually achieve that continuous learning goal.
That's the idea. And they put all this together in a proof of concept model called HOPE.
HOPO, what kind of architecture is it?
It's a variant of another architecture called Titans, but it's fundamentally a self-modifying recurrent system built using these NL principles and the CMS blocks.
Self-modifying, meaning it uses those nested loops to optimize its own memory systems.
Yes, it's self-referential in that way. It's constantly tuning how it learns based on its experience. That's what underpins the claim of unbounded levels of in-context learning. It's an AI that's designed to get better at learning while it's learning other things.
Like tuning its own engine while driving. Does it actually work? What do the results show?
Well, the results were promising. HOPE showed pretty solid improvements in language modeling, lower perplexity, meaning it predicted text better, and also on common sense reasoning tasks like PIQA, HelloSwag, ARCC.
Better than existing models.
Yeah, it often outperformed strong recurrent baselines, Models like the original Titans or RetNet, which are already quite capable but lack this deep nested learning mechanism.
So it suggests that just making models bigger isn't the only path forward. Making the learning mechanism itself deeper is another way to scale.
Absolutely. It adds a new dimension, right? Not just architectural scale, more layers, more parameters, but increasing the depth and sophistication of the learning process itself. Meta learning baked right in.
Okay, so that technical breakthrough, creating potentially non-amnesiac AI, a self-improving learner that clearly has huge implications. Let's shift to that economics of scientific inquiry idea. How does this change science?
It's a fundamental shift in the cost-benefit analysis that scientists do, consciously or unconsciously, when deciding what to research.
You mean deciding if an idea is worth pursuing?
Exactly. Is this theory, this experiment, likely to yield valuable knowledge? And how much will it cost in terms of time, money, effort? A concept is pursuit-worthy if the expected payoff outweighs the expected cost. DLMs, especially advanced ones like HOPE might enable, attack both sides of that equation.
Okay, let's take the first part. Increasing the expected payoff, or the expected epistemic value, EEV, as the philosophy paper calls it. How does AI make an idea seem more likely to succeed?
Two main ways: plausibility and fruitfulness. Take plausibility first. Look at AlphaFold again. Before, discovering a protein structure was this long, uncertain process.
A lot of guesswork involved.
Sometimes, yeah. Now, AlphaFold gives you a prediction that is often incredibly accurate. It's seen as an exceptionally useful hypothesis. It makes the idea of that specific structure highly plausible right from the start.
So the scientist isn't starting from scratch. They're starting with a strong hint, which increases their confidence that the experiment will actually confirm something valuable.
Precisely. The probability of accepting the hypothesis, given the AI's prediction, goes way up. That justifies the effort.
And fruitfulness.
This is where the AI doesn't just confirm an idea, but suggests new ones. Maybe it proposes a new mechanism for how a drug works, or suggests a novel experiment to try.
Like, have you considered testing this pathway?
Exactly. Systems are being developed right now to try and identify potentially fruitful research directions, maybe by analyzing existing literature or data in new ways. If an AI suggests something genuinely novel and insightful, that idea immediately becomes more pursuit-worthy because it holds the promise of truly new discoveries.
Okay, so AI can make ideas seem more likely to be right, or more likely to lead somewhere interesting. But you said the biggest impact might be on the cost side, decreasing the expected practical cost, EPC.
Oh, absolutely. This is where it gets truly revolutionary. DLMs just demolish the costs for certain types of inquiry.
Like the AlphaFold example again?
Perfect example. Experimental structure determination. Weeks, months, maybe millions in equipment and salaries. AlphaFold. Seconds on a computer. The cost reduction is astronomical.
And that database, 214 million predictions. You literally couldn't do that experimentally.
Impossible. It's a scale of knowledge generation previously unimaginable, and that's the key. When you lower the cost of investigating an idea so dramatically, even ideas that might have seemed only marginally promising before suddenly become worth looking into.
Because it's so cheap to just check.
Right. The barrier to entry plummets. Scientists can suddenly pursue a much wider range of hypotheses. They can explore more, faster. Even if the chance of success for any single one of those cheap ideas is lower, the sheer volume you can investigate changes the game. The overall efficiency gain is potentially massive.
More shots on goal, basically.
Yeah, many, many more shots on goal for a fraction of the cost per shot.
But this sounds almost too good to be true. Speed, efficiency, low cost.
Yeah.
Surely there are downsides. The sources mentioned illusions of pursuit worthiness.
Yes, exactly. All this speed and apparent efficiency comes with new kinds of risks. The AI can trick us, essentially. It can create illusions that lead us to waste resources in new ways.
Okay, let's break those down. What's the first risk? Spurious plausibility.
This is where the AI makes an idea seem more plausible, more likely to be correct than it actually is. It gives us false confidence.
Like the AlphaFold example again, you said it's not always perfect.
Right. It might confidently predict a structure for a part of a protein that's actually intrinsically disordered, meaning it doesn't have a stable structure. If a researcher takes that confident but wrong prediction as gospel,
They design experiments around it, spend lab resources trying to verify it.
and waste potentially months chasing a phantom structure, all because the AI gave them an illusion of plausibility. The initial prediction was cheap, but the follow-on cost is high.
Okay, false confidence. What's the second risk? Illusory fertility.
This is similar, but about the promise of future discoveries. The The AI flags an idea as potentially fruitful, likely to lead to new insights, but it's actually, well, junk.
Like an LLM generating research ideas.
Exactly. An LLM can spit out thousands of research questions or hypotheses. It looks incredibly fertile. But some early studies comparing these AI-generated ideas to expert-generated ones found the AI's ideas were often rated much lower in quality, novelty, and actual usefulness.
So you get this fire hose of ideas, creating the illusion of progress, but most of it might be noise, distracting from genuinely good ideas.
Precisely. It feels fertile, but it's actually barren. And the third risk, efficiency traps, sounds maybe the most insidious.
Efficiency traps. How can efficiency be a trap?
This is about the long-term effects on the scientific ecosystem. When DLMs make certain kinds of research incredibly cheap and fast, like prediction tasks, the incentive structure for scientists shifts.
People follow the easy path.
Potentially, yes. Why spend years wrestling with a really difficult, fundamental theoretical question like how proteins actually fold, the underlying physics and biology, when you can get publishable results quickly and cheaply just by running predictions using an existing tool?
So the easy research crowds out the harder, potentially more important foundational work.
That's the fear. The community might get really good at applying existing AI tools to generate lots of low-hanging fruit, but neglect the deeper, slower theoretical work needed for the next generation of breakthroughs. We become efficient at solving yesterday's problems, but trapped, unable to tackle tomorrow's because we haven't invested in the fundamental understanding.
That's a sobering thought. A whole field potentially getting stuck in a local optimum of easy results.
It's a real risk that needs careful consideration as these tools become more integrated.
Okay, so wrapping this up, this deep dive has taken us from the memory problems of current AI to this idea of nested learning, adding a whole new dimension, as you said, to deep learning.
Yeah, it's a shift from just scaling up the architecture, stacking more layers, to scaling up the learning mechanism itself, making the optimizer, the memory systems, deeper and more dynamic,
We're moving conceptually from these sort of static amnesiac LLMs.
to potentially self-modifying systems like Hope, systems that can genuinely learn how to learn better, constantly rewriting their own memory strategies as they go.
Which leaves us with a pretty profound question, maybe something for you, the listener, to think about.
If we build an AI like Hope, one that can continuously, autonomously rewrite its own core learning algorithms, its deepest memory consolidation strategies, how do we ever establish a stable baseline?
How can we reliably evaluate or trust or ensure the safety of an intelligence whose fundamental operating system is constantly changing itself in response to new data, potentially in ways we didn't predict and might not even fully understand?
That's the challenge, isn't it? How do you align or control something that is perpetually optimizing its own foundations? A fascinating and maybe slightly unnerving place to leave it.